So for the second half of the show, I'm delighted to introduce Ken Miller from the Department of Earth and Planetary Sciences at Rutgers University. Ken is by training a stratigrapher and geological oceanographer, and he has been working for the last 5 years or so.
Since 2008.
2008, on carbon storage part of the problem. So without further ado, Ken.
Well, I want to thank Paul and Bea for the invitation to speak here. And 2008 is an important date. We had a symposium sponsored by the Rutgers Energy Institute on carbon sequestration. And that led to us basically getting funded by both from DOE, managed by Patel, on two different projects that I'll be talking about today. But it's also an auspicious time. Let's see if this works. The sound file, you have sound on?
Let us fund new technologies that can generate coal power while capturing carbon emissions.
That was President George W. Bush in 2008. That same year, candidate Barack Obama visited coal country in Virginia and said this.
We figured out how to put a man on the moon in 10 years. You can't tell me we can't figure out how to burn coal that we mine right here in the United States of America and make it work. We can do that.
And now President Trump is on board the coal train.
My administration is putting an end to the war on coal. Going to have clean coal, really clean coal.
Right now, burning coal contributes more carbon dioxide to the atmosphere than any other industrial process. There is technology to strip the CO2 from coal and either bury it or use it elsewhere. The federal government spent 20 years and billions of dollars to make it work. The result is the Petronova plant.
So we will go to the Petronova plant later on in the talk. In this 10 years, we have faced many challenges in both the implementation and policy aspects of carbon disposal. So when asked, what should we do to address our energy and carbon dioxide issues? Should we have better efficiency? Should we have disposal, geological disposal of carbon dioxide? Should we have disposal in forest and soil carbon? The answer to that question is yes. The energy stabilization wedges of Pacolo and Socolo show that very nicely. Geological disposal is a needed part of the wedge moving forward. Real quick on capture, this is something I know very little about, but basically 1,000 stationary point sources, mostly power plants, comprise about 30% of global CO2 emissions. Now we can capture this, as Klaus has demonstrated, and dispose of it. We also can capture from large point sources, the power plants, either post-combustion using membranes and other technology, pre-combustion, which we take either coal, biomass, biochar, or natural gas, and we separate out the hydrogen and burn the hydrogen cleanly, producing water and capture the CO2. The introduction was about coal, and if we're going to have clean coal, we have to do this if you have such things as clean coal. But we don't necessarily have to do this with just coal. We can do this with biochar, bioenergy, or from air capture. So what is sequestration or storage? It can be done biologically, reforestation. I talked about aquatic biomass. One part of the problem with this is the volume. There's a volume problem here that you can only store about 0.4, maybe a gigaton per year. It may be scalable slightly higher. But with geological storage, we can do a bit more, as shown in the wedges. Now, it was mentioned injecting CO2 into the oceans. That's just a really bad idea. It's been demonstrated, and there's an article on Oceanist I could refer you to. We also can do accelerated weathering of basalts or serpentines, and that's an interesting technology that's discussed by Peter Kellerman and Jorgen Matter at Lamont. I'll refer you to that. Today, what we're talking about is the subsurface storage of supercritical carbon dioxide. Supercritical storage means that we're storing carbon at a point with sufficient depth and temperature that it becomes a supercritical fluid, And it basically means that we can increase the storage. So this is a volume that by 800 meters depth, that volume of CO2 is decreased to this level. And this level of supercritical sequestration is typically at about 800 meters. So we have to get at least 800 meters depth. It's also a story of essentially reverse petroleum engineering, and you need two things. You need a reservoir and you need a seal. And the title of this talk was Geology Matters. We saw this picture before of where we could dispose of CO2 geologically. We're focusing today on deep saline formations here, but there's also the storage, which is done by, it was called EOR, which stands for Enhanced Oil Recovery. One of the take-home messages here is that every current project that is moving forward and either in implementation or coming down the line is an EOR. So there's a positive, we are sequestering CO2. There's a negative that we're extracting oil and gas to burn again. So again, I said this is reverse petroleum 101. We need a reservoir, which is a porous, 30% porosity, permeable, over 100 millidarcies, typically sandstones or limestones. The reason why we focus on saline reservoirs, as I said earlier, is that we don't want to use potable water. We need a seal, a cap rock, and a confining unit, which is typically a tight shale. There's a number of places that are quite suitable to do this in the United States. Obviously in places where we have 800,000 wells in Oklahoma or 110,000 wells in the Michigan Basin, we can put these into old oil fields or use them for EOR. The eastern part of the margin of the U.S. here, is also a potential area, and I'm going to use that as a case study today. Starting in 2007 and 8, we began to evaluate this region's potential. This is Andrew Kolpez, who was supported as an REI summer student to map the various point sources of CO2. We updated this more recently. There's a couple suitable power plants here that could be retrofitted or replaced. One of those is at BL England plant. In fact, one of the reasons why they're building a pipeline across the Pinelands is to supply natural gas to this really dirty coal plant. Indian River Power Plant in Delaware is another. Both of these lie within this seaward of this line of supercritical sequestration, which means that there's sediments here that are suitable that are deeper than 800 meters. So this is a geological cross-section that goes along the coastline from New Jersey through Virginia. It just shows that there's a big, thick wedge of sediments. Particularly, here's the 800-meter line of supercritical sequestration. We looked at the geology of this. So this is a well-logged transect that goes from Buena down to Anchor Dickinson, Cape May well. This black areas, those are sands picked out on logs. So these are really thick, blocky sands that are well confined by overlying strata. Local units are called Potomac Formation, Wastegate Formation. It has nothing to do with the fact that this actually is a very good place to put our CO2 waste. We also extended this in, jumping around here, we extended this into Maryland. This was an REI summer intern, Colleen Walsh. So in Maryland, there's also the very thick sands of the Wastegate and Potomac, which can be used to store CO2. And so we did a volume estimate of how much CO2 capacity there is to store onshore in this region, and it's about 21 gigatons of carbon. So most people have been referring to CO2, gigatons of CO2, so multiply 21 by 3.6 to get that equivalent. So it's a boatload that can be stored. It's one of the better prospects. In Michigan, they're looking into the Mount Simon sandstone. They're doing some injection tests. It's about double the capacity of this region, but we are also closer to the sources. We'll come back to this in a few minutes. One of the difficulties of doing this in the East Coast is basically political. We don't have the culture of having 110,000 wells like in Michigan, and we'll see how that comes into play later. The offshore region is probably more suitable. It is a good storage location. Our preliminary estimates is that the volumes that we could store are even greater than onshore. It doesn't conflict with oil and gas resources, so the problem of pumping supercritical CO2 into a reservoir is that if there's methane present, you have to capture that methane. These units I refer to the Logan Canyon sandstone and the Mississauga sandstone offshore. Have no gas in them. There's voids of public perception. It's called NUMBY. We've all heard of, it's not under my backyard. It's opposed to NIMBY. And it mitigates concerns regarding earthquake stimulation. I'll come back to that in my last few slides. So this is the team. We're funded by initially the Midwest Regional Carbon Sequestration Partnership with the New Jersey Geological Survey and New York Survey and others. I bet you didn't know that New Jersey and New York are in the Midwest, but we were. However, New Jersey, for political reasons, pulled out of the consortium, and so did New York. We'll come back to that. So we represent New Jersey as the Rutgers team. An RFP was issued by DOE a year and a half ago. We responded with Patel and a consortium including Delaware Geological Survey and Pennsylvania Survey to do offshore work, and this is the team of graduate students that I have working both on log examples and on seismic examples. I'll give you a couple quick updates. The regions that we have been working on, we extended from the offshore region. So a trough, it's called the Baltimore Canyon Trough. It's just a big, thick accumulation of sediments, up to 16 kilometers of sediments out here. And there's also another basin to the north called the Georges Bank Basin, separated by the Long Island platform. So this area was explored for oil and gas, LNG, in the late 70s and early 80s. One of the big targets was the Great Stone Dome, a geological structure offshore of New Jersey here. The COSP-2 is a reference well that we'll spend a little time on. And actually, there was natural gas found in these 4 offshore outer continental shelf wells. But these were dry as it possibly be. And the nice thing is with the COSP-2 well, we've been able to provide really good ground truth for the first time. This was work done initially by Chris Lombardi, a graduate student here. This is a log just to show you how this works. When we colored it in dark colors, that's a finer grain. So this is a shale, this is a sandstone, this is a sandstone. And we were able to register, this is a black laminated shale here. These are tidal sands, these are foreshore sands. So it gives us a certain amount of predictability. We do what's called sequence stratigraphy. We identify unconformities. And those unconformities, shown here as red lines, are basically time planes, and we can use biostratigraphy to confirm that. So now you're here listening to the stratigraphy professor tell you how the geology works. But this is a beautiful blocky sand in here, which is ideal for carbon sequestration. Measurements of the permeabilities in here are on the order of 1,000 millidarcies, and it's very high porosities. And so this is an ideal reservoir in this sequence here and in the underlying sequence. Now, this is a very busy figure, but this shows, just follow the red lines from the Great Stone Dome going out, and you can see the grays are the sands, and we can trace these around. The red dots are our biostratigraphic control that tell us this is the correct correlation. And it tells us that there's a great deal of predictability that this overlying shale will confine these sands here, as will these shales up here. And the sand here and the sand there, that they're the same sands. And this is opposed to older correlations, which just try to line the shales up. And so they line this shale up with that shale up, and that shale, with that shale, with that shale. This is a miscorrelation. And it's important because you want to make sure when you pump into a sand here that you are fully confined. And we're final geology story before we get into some of the politics and other problems. We can use seismic profiles. This is the Great Stone Dome. This is a sonogram of the Earth. This shows that these yellow lines are seismic sequence boundaries that we identify by reflector terminations. That gives us great confidence. We're able to then correlate the things that we did on the well logs around this region We can map the units, we can do thicknesses of them, and we can look for things like faults. You don't want faults and avoid faulted areas. One other advantage of this area is there's only 33 wells drilled in the whole area. This is the mobile 5441 right on the structure. So when you go to an area with 100,000 wells like Michigan, you worry about the possibility that fluids pumped in will find a previously drilled well and escape. So the geology is ready for the mid-Atlantic offshore. It's got good reservoirs, good seals, and good local point sources. So what's next? What are the political and economic challenges in previous and current projects? So Sleipner has been going and injecting into the North Sea since 1996. This is a gas field in the Norwegian sector of the central North Sea. The gas is basically produced as methane, but it has a high carbon dioxide content, that is a wet gas, of about 4 to 9%. So Statoil was spurred by a carbon tax to capture and store the CO2 in this reservoir here, it's Usiris sandstone. And they're basically injecting about a megaton per year. So this is a very successful project, and they've been monitoring, and the project has been ongoing. So that prompted SCS Industries to come in and propose to do a major project in New Jersey, to build a power plant in Linden, New Jersey, and pump offshore to do very similar to what was done by Statoil. And this is Dan Schrag from Harvard, who is their geological consultant on this project. It was called the Purgen plant, and it was by SES Energy Limited Liability Corporation. It was proposed at the same 2008 window that we started out with. And they need a very high efficiency plant, so they're going to build a plant with 40% efficiency. They were going to do 90% capture, okay, by basically pre-combustion combination and produce hydrogen. It would be a 500 megaton plant with 5 megatons of CO2 per year. It would be the first commercial power plant. It would have been. They were going to do this with $3 to $5 billion of private capital, and their business plan was made viable because they were going to continue to generate at night, but basically use the hydrogen either for fertilizer or, in a different world perhaps, use it to make hydrogen fuel cells. They were going to build a $700 million pipeline that was included in the $3 to $5 billion capitalization offshore and sequester. There's the usual suspect of the Cosby 2 well that I just took you to. The plan was a good one, but it ran into opposition from local officials. They were going to assume all the liability of the former DuPont Superfund site in Linden, but the activists in Linden opposed this. New Jersey Sierra Club opposed it. One of the reasons why is because they were using coal. This is Corey Havlati, who was a REI summer intern with Bob Kopp and I, and she did an analysis of this social political reactions, doing interviews and going back over the project. It occurred, the economic feasibility, if you know what happened in 2008, we had the fracking revolution, and the price of natural gas dropped a factor of 2, and coal became less favorable. There was the failure of the expected federal climate change legislation assigning a price to coal, and there were political aspects. So initially the New Jersey DEP opposed this, and then Governor Christie came out actively against it, and the project was dead. So Purgen and SCS picked up and moved to California, and they started an EOR project in California. That project was killed on March 3rd, 2016 by basically political opposition. I don't think that carbon sequestration isn't going on. It was shown earlier, the Gorgon project. This is the largest carbon dioxide injection project on the planet. It is being done in northwest Australia. There's a field here, the Gorgon field, which has a lot of wet gas. And so they're capturing the CO2, and pumping it in. The project is near implementation. It's well along. They were going to dispose of the carbon dioxide into Cretaceous sands, very much like the Cretaceous sands I just talked about. This is Andrew Kolpez, who I mentioned who was the REI intern. Andrew works for Chevron on this project now and lives in Perth. It also goes back to the current ExxonMobil president, Stephen Greenlee. And Stephen Greenlee worked with us in offshore New Jersey, not from an oil exploration perspective, but from an academic perspective. But when Steve was here at Rutgers 3 years ago, he gave a very interesting series of talks, but he made the point that Exxon is the largest sequesterer on the planet at that time. And of course, Secretary of State, former CEO of Exxon, Rex Tillerson, said in Forbes in 2016 that Exxon is involved in a third of the worldwide projects to capture and sequester carbon dioxide. Now they're doing this again, and when Steve told me this back a number of years ago, is because ExxonMobil had inherited the Mobil fields in Indonesia, which the gas was very wet, and so they were required by the Indonesian government to sequester. So regulations are important in terms of making the right thing happen. It helps to also get subsidies. We started out hearing from NPR from May 1 about the Petronova EOR facility. I think Paul cringed when I mentioned that this was EOR, okay? And yet it is better than not having capture. This plant is online. It captures more than 90% of the CO2. It's sequestering 1.6 megatons per year. They're using the captured CO2 to enhance production in the West Ranch oil field. Thank you for your contributions. $190 million came from the Clean Power Initiative of President Obama. It was, and one of our Battelle people vetted my slide and said, make sure you mention that this was constructed on time and on budget and performing the specs. So that's the good news. Now we're going to start hearing about some of the bad news. Kemper is nearing implementation. This is in Mississippi, again, EOR into 2 oil fields here. It's a lignite-fired power plant, so it's one of the dirtiest coals you can use. They did receive $270 million of your tax dollars to implement this plant. Cost inflated from over $2.4 to $7 billion to cost overruns. So if you follow this in the New York Times, this is quite a saga with this plant. In project management issues, it is already 3 years delayed. Similar story in our Canadian friends. Boundary Dam went operational in July 2014 in Saskatchewan. It was the first plant to capture carbon on an industrial scale. SCS would have beaten them in Linden, but they sell the CO2 for EOR in Weyburn Fields to offset the cost. It was a $1.4 billion Canadian, $240 million of which came from the Canadian government. So now I want to pose this. I originally had on this slide the weaknesses, and these are true weaknesses. It was plagued by problems. It had cost overruns. The Economist ran an article about how it had negative earnings, that is earnings before interest and taxes. It doubled the local price of electricity. The shocking fact, to a certain extent, I think, is that only 50% of it's being stored. The rest of it's being captured and released. Now, there's two sides of a half. Is it half full or half empty? It's still sequestering a boatload of carbon. It's one of the first plants to do this, okay? One other negative you would read, that people say, well, you're subsidizing oil extraction. Yes, that is true. The strength, though, is there are strong policy drivers in Canada to reduce emissions. It overcame many of its initial challenges. It captured 800 kilotons in 2016. It is the cleanest coal-fired power plant in Canada. So Germany was leading the efforts initially, and particularly doing a Schwanz pump. They had a steam generator capturing 100% of the carbon dioxide, and they were going to transfer this technology to Jonswald. But this project was canceled due to opposition and the fact that the German government could not delineate a legal framework for carbon sequestration. Vattenfall is a developer from Scandinavia. They cut their research on CCS completely out. And it's interesting that the website that I got some of this information from is the Carbon Capture and Sequestration Technologies website at MIT, which is now offline. They are no longer supported. So we heard about the concerns about earthquakes, and this is an important concern. This is a paper by Mark Zobak, a National Academy of Science member, on earthquake triggering large-scale geological storage of carbon dioxide and or fracking. You may know that disposal of fracking fluids in Oklahoma has increased the number of earthquakes significantly, mostly in the lower range of 3s. Geology matters, folks. If you go to Texas, which has the same geology but a different stress field, the injection does not cause earthquakes. So I pinched this from Dan Schrag. When they were getting near implementing this project offshore, he worked with Schlumberger Carbon Services, which is no longer part of Schlumberger. They cut out their carbon storage budget too. And they did a model of injection, those Logan Canyon sands I boringly took you through. And there's 5 slides here, but it really is a movie. 5 years, 10 years, 20 years, 30 years, 50 years injection, and then after injection stops. So those are the pressures that are developed, and they approach 1,000 megapascals with the stress field here. I'll take Dan's word at it, that they will not generate earthquakes. So, the conclusions. Geology is ready. Onshore, we have suitable storage in Beasley's Point, New Jersey, and Indian Point, Delaware, but I don't think it's feasible due to concerns about not under my backyard and opposition from green parties. The Logan Canyon sands offshore are a world-class target, and you could have multiple injection sites, Great Stone Dome, Outer Continental Shelf. We can move further south toward Maryland. But there is political opposition to geological storage offshore. Then again, the Purigen plant could be done with natural gas. Private discussions I had with people in the Sierra Club was one of the big complaints about Purigen was that they were using coal. And if it was done with natural gas, it might be acceptable. But there's a huge amount of inertia to get over this bump to get this done. One of those points was made earlier was that economics are not there without a price for carbon. SES was going to do this, but I also remind you that SES wasn't totally blocked entirely by the governor. It had to do with economics. We had the great economic turndown of that year, and also they couldn't get the capital that they wanted. But they had envisioned being able to do this with private capital. And I'll leave you with the final thought, good or bad or indifferent, all current projects are EOR, or wet gas recovery. In the last slide, I did want to mention that this is in memory of Chris Lombardi, who passed away unexpectedly on November 29th, 2016. He's the one who did this initial work. We've gotten it accepted to Journal of Sedimentary Research. Chris is posthumously going to be awarded his degree on Friday. And he was nominated by one of our colleagues at the Pennsylvania Geological Survey for the American Association of Petroleum Geologists Environmental Geology Award, and he was awarded that in April, and we would present that to his wife later this afternoon at our awards ceremony in Earth and Planetary Sciences. Thank you.
Thank you very much. Thank you, Ken. We have time for questions, so yes, Jeannie.
2 questions about offshore. First one, distance offshore, and secondly, risks.
So the distance offshore is about 90 miles. It's 80, 90 miles to cost B2. The risks. Initially, they wanted to do this at the cost B3 well because it's in 800 meters of water, and believe it or not, with that increased pressure and temperature, okay, the equation of state was mentioned that carbon is typically about 60 to 70% the density of water. At those pressures and temperatures, Schrag computed it was 90+%, and his model suggested that the plume would not. You try to do this on land, you are putting a balloon underground. It wants to get out. Out on deeper water, it's not a balloon. But their concern was on a slope, it is a slope, that if something goes wrong and it stimulates a landslide, hello tsunami, okay? There is a real risk. Out on the outer continental shelf, if it vents, it's not a problem. Now, the reason why the other risk is if it did vent, it would potentially locally injure bottom-dwelling organisms. That's why you don't want to pump it into the deep sea and just leave it in the ocean. Schrag also had done the modeling. Initially, they thought they'd had to put release wells in. As part of that simulation I just showed, the stress field doesn't require release, so there's no risk there. There's no risk of existing wells, and so what his simulation was, this is done very quickly. This needs to be done. Petroleum engineers have to come in and do this with a more sophisticated model. But I think in terms of risk, it's pretty low.
So vis-a-vis that, if this would not apply very well on the west coast of the United States, if I understand this, right?
Right.
So this is really an east, because you have a passive margin here and a much wider shelf. This is a more ideal setting for this type of disposal?
So when Schrag presented this to the drilling community in a meeting in 2010, a structural geologist from the West Coast, Emily Brodsky, said, "It's going to cause earthquakes." And he goes, "But Emily, not here." And so he went back and did this work to show that the stress field is such that it wouldn't cause earthquakes. But that was my biggest concern. The geology is there. These are really porous sandstones. I was shocked. I held it in my hand from one of those cores and so, my gosh, this stuff really is great. And it's beautifully confined by thick shales. In southern New Jersey, we did it onshore. We know that those confining units are really good onshore. In Maryland, there's some debate, and we published this with the Maryland Geological Survey, as you go up dip, the possibility that it may not be confined. So we'd place Maryland in a higher risk category onshore than New Jersey onshore. So the point, the title was a kitschy title, because Paul's been telling me for 20 years, biology matters. So this title is to remind people that in order to do this, you have to have the right geology. So I think that answers the question.
Thank you. Any other questions? We'll come back to a panel discussion a little later, I think.